Welcome to the 12th lecture of our course, Applied Statistics. इसको याद है लास्ट लेक्चर हमने क्या किया? मेन थीम क्या चल रहा है आजकल? कौन सा मॉड्यूल चल रहा है? डिस्ट्रीब्यूशंस वगैरह हो गई थी. उसके बाद we went on to the fourth module of the course, where we said that we will look into how do we use statistics, that is measurements or observations from real data, right, to make assertions about the mean, the variance and those things, right? So we have been saying that the course is based on 5 modules. The first module, again, assigning probabilities. Second module, collecting probabilities, PDF, CDF, all that. Yes, and then examples of those PDFs like uniform, normal, geometric, exponential, Poisson, all that. The third module, extracting key information from the PDFs, mean, variance, covariance, right? Their interpretation, how to work with them. The fourth has been to now redo all that we did, but assuming real constraints. What are the real constraints? Real constraints are that many problems of assigning probabilities, working with probabilities, or working with mean, variance, and so on, are not as simple as a game of lottery or throwing a dice. Yes? So we had to work with real data. And in that fourth module we said, okay, what you will do, let's say, I've been giving this example of, we want to find the average height of adults in Swabi. Yes? So this population would be around, let's say around 1.5 million people, adults in Swabi. So would you go and measure each one of their heights? That would be too much, right? So these are the real constraints, and the fourth module will be calling it getting real, to handle realistic situations. Yes, and there we get the concept of a population. Yeah, the population was, let's say in this case, it's all the 1.5 million adults living in Swabi. Yes, now we realized, and the last 2 lectures have been on that in good detail, that we will not be able to, in many cases, do this entire thing. So this population of 1.5 million adults, and now we will go to all of them, so we will have to strategize. What is our strategy? Take a sample, right? Subset. Let's say measure heights of 5,000 people in Swabi, and try to guess from there what's the average height, for example, or the range, the mean, the mode, all that. So then the problem was, we did say that we will try to take a random sample so that our results can be somewhat reliable. The problem with that was that different people can take different samples. 1.5 million लोग हैं, आपने 5,000 चुने हैं. Maybe you select one set, you select another set, right? Now would all of them, if they calculate, so let's say one of you selects, let's say you both each selects 1,000, 5,000, and you calculate the sample mean, that is the 5,000 heights that you measured, 1 over 5,000, sum all those heights. I will put a 1 here to represent one of you, right? One person doing this estimate. Now that person will get I is equal to 1, 2, 1, 2, and say n is 5,000. Now even if another person, another student takes a set of 5,000 randomly, they will not come to this exact same conclusion unless they take the exact same persons, which is very unlikely because they're doing it randomly. So one of you, let's say, takes this sample, another one among you takes this one, a different sample, let's say, of comprising of these people, 5,000 people. Yes. Now each one calculating the mean will most likely end up with a slightly different value. Yeah, or could be extremely different, depending on how much variability there is. So we said in our nomenclature, we said that this thing we will call population. Yeah. All the possibilities in this case. This is kind of your sample space. Yeah, this is the population. Then we said what you pick from it, we will call it sample. Yes. Now the statistics of the population, for example, mean, variance, mode, covariance, many others, we will call them the true statistics. So the mean of the population, that is if you were to measure all 1.5 million people height, adults heights in Swabi, then you will be calculating the population mean or the true mean. Yeah. What you are trying to guess from here is to take a sample, find the mean, and hope that it is close to the true mean, right? And for that, of course, we want to say replace the hope with some mathematical qualifications. Yeah, so we added several discussions on what is a good estimator, how to test the quality of your estimator, what is a good estimator of the mean, what is a good estimator of the variance. Then we saw that since the estimates themselves are randomly distributed, as soon as you see that a variable is randomly distributed, your first thought should be, what does its distribution look like? PDF. Yes, we have studied uniform, normal, Poisson, all that. Yeah. So we saw three cases. We saw the cases where the distribution was standard normal, then there was distribution was t distribution, then there was chi-square distribution. We did all of that. Now, the next thing we want to do in this fourth module, which is the last topic in this module, has to do with something called classification theory. Okay, and a lot of modern machine learning, AI, is basically classification theory. You're trying to classify, is this image of a person or a gorilla, for example. Yeah. So you are mostly classifying using your machine learning AI algorithms, and what we discussed today is quite much a foundation of that. So often what we are interested in is making assertions or claims about the population. Okay, and based on those claims we want to design something, make a decision. So we want to know the veracity of our claims. Is my claim good? How do I test? Okay, all of this falls under the category of hypothesis testing, which is the topic of today's lecture. So for example, maybe I make a conjecture or a guess that most adults in Swabi are taller than 168 centimeters, for example. Now that is my conjecture, okay, my guess, my claim. Technically we call it my hypothesis. Okay, my hypothesis could also be that the average height of adults in Swabi is 168 centimeters. Yeah? So there are so many different claims I could make about a population, and they would be considered different hypotheses. Okay. Now, what is the problem with that? How do we check the veracity of a hypothesis? Because if I can know that my claim is most people in Swabi are taller than 165 centimeters, if I can say that there's 90% likelihood that this claim is correct, yeah, then I can make a lot of decisions on that. Okay, so Similarly here, what we want to be able to see, okay, let us see what can we do to check those claims. So let's say, let's go with the claim of, I need some space here, so we'll take this away. This we have done in detail, so I'll just use this idea again. My claim is that the average height of people in Sawabi is 165 centimeter, let's say. Now, how do I check this? Let's say I ask each of you to go and independently try to verify it. Yes? Now, if all of you go and check the heights of all 1.5 million people, you will all come to the same conclusion, whatever that is. And you can easily say, am I right or am I wrong? Yes? But since you will be sampling, one of you takes this sample of 5,000, one of this take this sample of 5,000, you're not restricted to 5,000, but just to make it easy, let's fix it that each one of you have to measure 5,000 adults in Swami. Yeah? Then some of you will find your mean to be here, others will find it here, some will find it here, some very less likely that any of you will get the exact mean. And this is what we covered in the previous lecture, that your estimate is a random variable. Yes? So some of you will be here, most will be hopefully close to the mean, we also discussed that, and then some will be far away from the mean. Did they do something wrong? Well, no. This is how randomness works. You could have a sample whose average height is much taller than 165, 170. Then you conclude in your case, those of you, now firstly it's important to see here that in this kind of a situation, getting the exact value is of course very unlikely. So maybe we can make things a bit simpler. Yeah? Maybe I can say, okay, if you conclude that, or if you find a mean height between 164 and 166, this is arbitrary, you have to decide your tolerance. Yeah? If one of you concludes, or those of you who find an average height between 164 and 166 will say that I was right, and the rest will say I was wrong. Yeah? Still, there are chances some of you will conclude that I was wrong. Yeah? So how do we test? How do we conclude that? How do we make a decision? Was my claim correct within this range or not? What is the likelihood of my claim being correct? Now, of course, that is one issue we need to resolve, and let's now write these out a bit. Let's write it a bit formally now. So firstly, the field is hypothesis testing. Okay? And it usually starts with this. Now I'm trying to make what I just said more formal, and then we will continue from there. So it starts with us making a claim about some property of a population, a conjecture about some property of a population, like I made that the average height of adults in Swabi is, let's say, 165 centimeter, whatever claim I made. Yeah, this we call the null hypothesis. Okay, now these are the terms that we should slowly get used to. Well, H naught, the null hypothesis, that is your main claim. Okay, then we often have an alternate hypothesis. Okay, alternate hypothesis can simply be the complement of this. Okay, it could be saying simply that mu naught is not 165. And I was wrong in this sense that it was not 165. So this is called null hypothesis. This we call the alternate hypothesis. Okay, the alternate hypothesis could even be very specific, like H1 could say that mu naught is actually 170 centimeters. Okay, so in some cases it's just saying that no, H naught is not true. In other cases it's saying something else, but of course the two cannot make the exact same claim. Yeah, so it can be very specific, or it could be just saying that the H naught is untrue, whatever falls in there will be in this. So let's stick to some simpler case here. Okay. Thank you. ये pre-selected हो ना वो function नहीं करता जब तक change ना करें. Okay, so null hypothesis, alternate hypothesis. The alternate hypothesis, already I said, can take multiple forms. Now it could be the proper classification problem actually can have multiple hypotheses. Null, alternate 1, alternate 2, alternate 3. Thankfully in this course we will not go there. Yeah, we will stick to the null and the alternate. As I said, alternate could be as simple as saying no, not H naught, or it could be very specific, saying if H naught, one of you is making hypothesis that height is 165 centimeters, then the other doesn't say no, it's not. It says no, it's 170. So it can be specific, or it can just be a simple complement of H naught. Then if you notice that we set some sort of a limit or a range in which we were going to accept that I was right? So if this was 165, I said if you find the mean to be between 165 and 166, you conclude that I was right. One of you concludes, whoever lands here concludes I was right. So this kind of region around the null hypothesis has a name. We call it critical region. So I am giving you the terminology of what I just told you. Yeah, the general example. This is called the critical region. Inside it, you conclude that H naught was, at least one of you concludes, whoever falls. So remember, many of you are taking your samples. Some of you will find the mean here, some will find it here, some will even find it here. Yeah, those of you, if all of you are sent out to Swabi, measure 5,000 people at random, take their average. Yes, so those of you who conclude or find your X bar within this critical region say I was right. Those of you who don't find it inside it will say I was wrong. Yeah. Now how do we conclude that I was right? Not easy. We could set we could set a significance level. Let's say I could say if 90% of you come back saying I was right, then I was right. So there is no, this is probability theory. Yes, 100% वाला कहानी नहीं है. अगर होती तो हम ये कोर्स ना पढ़ते. Rest of math is good enough. Yeah, this is all probabilities. So let's accept that then. So null hypothesis, alternate hypothesis, critical region. The limits of the critical region are called critical values. Again, not the critical values of the maxima, minima. Yeah? This is probability theory. So just now we saw another concept, which was significance level. Yeah. So how do we conclude I was right? Let's set a significance level. All of you go measure 5,000 people's height, random samples, each one take a different sample, and if 90% of you find the average to be in the critical region, I was right, with a confidence level of 90%. Yes, of course we would like it to go towards 100, and we would not like to make this range too big. So critical region, significance level, all these terms are popping up, and of course we will write them mathematically also. Now as I showed you here, because the estimate of the mean is a random variable, even if I say with 90% confidence interval or confidence level, significance level, that I was right, 10% of you will come to a different conclusion. Your mean will be here. So 10% of you will wrongly think that I was wrong when I was actually right. But more interestingly, even if I was wrong, there is still a percentage of you who will come and say I was right. It's a different kind of mistake. Yes? So why would that happen? Let's say let's say I was wrong, and the average height of people in Sawabi does not fall here. It's not 165 and not in the critical region. Let's say it was sorry 175 and 170 centimeter. Now again, all of you go, check this thing or find the remember, you are checking my hypothesis. So all of you go and you calculate these things. Now those of you whose calculation or samples fall between 164 and 166, because it's a random variable, it has variability. If the true mean is 170, most of you will be here actually. But there will be some of you who will fall further there, or this is the bell curve. We have seen for the estimate of the mean that it has a bell curve, the Gaussian curve. But notice what's going on here. While most of you will conclude correctly that I was wrong, there is still chances for some of you whose calculation will fall within that range, and you will wrongly conclude that I was right, even when I was wrong. So there are two types of mistakes that can happen. So today we will see these precisely mathematically, write them out. Okay? At this moment I am just developing the language, the concepts needed to talk about hypothesis testing. Kya aa gaya? There is a conjecture about a population. So let's start zero. There is a population. There is a conjecture about a population. We call that hypothesis. There is an alternate conjecture about the population. We call that the alternate hypothesis. Then often to say that a particular sample verifies my claim, we often need to design a critical region. If it falls in the region, it's in my support. If it falls outside the region, that sample or that result is against me. Yes? Okay. So then we get the idea of critical region, critical points, the ends of the critical region. Then we said, now falling inside, how many should fall inside for me to finally conclude that I was right? There you have to define a significance level. If you want to say that if 90% of them fall in this region, then I was right, then you're saying with 90% surety I was right. Yeah? So you can increase or decrease that. But then with that, we also saw, okay, what kind of mistakes can we make? We saw one type of mistake was these guys, let's say I was right. Yeah? But these guys, these 10%, are wrongly concluding that I was wrong. So they are rejecting me wrongly. Yes? Whereas, let's say I was wrong. Then there is some percentage who will fall in my range still. Yeah? And those guys will wrongly think I was right and I was wrong. Yeah? So types of errors. All of this now we go on to put in more mathematical notation. By the way, the hypothesis can take different forms. Like you could make a hypothesis that most people in Swabi support party X, political party X, or vote for political party X. Yeah, could be that the COVID test you just took said positive, and the null hypothesis is that the test is right. Every test has a probability of being wrong. इसलिए दो दफा भी करते हैं वो chances कम होते हैं. Now there can be many different null hypotheses. It's not just these heights, or it's a huge range. It could be a hypothesis that the picture I just took has inside it, let's say a bicycle. There is a bicycle in the beach. That's null hypothesis. Then alternate hypothesis could be that it's not a bicycle, or it could be that it's a motorcycle. Yeah, depends on your application. What are you trying to build? Right, and neural networks make this task very easy. But one person can program a fixed neural network fine, but to really understand and to really contribute to that theory or to really interpret the results, you need these concepts, even in neural networks. Okay, so it's good. It will help you to pay attention no matter what field you are in, because all modern engineers are going to use machine learning, AI, neural networks. Right? It's like a calculator now. So it's good to have a clear understanding of what's going on. So let's come back to this type of error thing first. As soon as you make a hypothesis, yeah, then the universe kind of splits into 4 possibilities. Yeah, the first possibility, this is your world or your conclusion, and this is the reality, which of course you don't know. Batao to masla hi bani. Yeah, so we have to talk about this probability. Your world or your conclusion might be with 90% even, or whatever percent you wanna use here. You may say, okay, I accept H naught. Based on your calculation, confidence interval, everything, you say H naught is correct. My hypothesis was correct. That's one conclusion you could reach. Or data may not support it. You said 90% and more than 90, less than 90% of you come to me saying that you were right. So then I don't conclude in favor of this. So that would be, I reject H naught. Now these are 2 possibilities. Yes, either we accept H naught or we reject. Now what is in the real world? Real world could be that H naught was true or H naught was false. Two possibilities. Okay, either it was true or it was false. So where are we right? Let's see here. If you accept H naught, yes, and the reality is that H naught was true, did you make the right decision or no? Was your conclusion correct? Yes or no? So you conclude that H naught was correct. Yes, and in reality H naught was correct. So you were right. Yeah. So here you are right, and we call this true positive. True positive means that you concluded in favor of null hypothesis and you were right. Yes, but it could be that you reject H naught. You say no, data doesn't support it. With our confidence level, I decided I cannot support H naught from there. But in reality, it was true. Okay, then you have false negative. Wrong decision. Yeah. What is it? You concluded based on your analysis that H naught has to be rejected. It's incorrect. But in reality, it was correct. So we call that false negative. What else can happen here? यहाँ क्या हो रहा है? ये जो तासिफ है, read it out. What's in this part? You say you were right, yes, but in reality, you were wrong. Yeah. So this is again a case of a mistake. Yes, and this is called false positive. Positive means you concluded in favor of H naught, but you were wrong. Yes, this is so these are 2 errors here. What about this? True? Yes. So this is correct because you said H naught is not right, and the reality was that H naught was, in fact, false. So this was true negative. You said it's false and it was truly false. Yeah. So where do you want to be mostly? On this diagonal? Yes. You don't know. Both of these kinds of mistakes are wrong. Yeah. Now there are two different kinds of mistakes. Yes. एक में ये है कि someone had COVID and you said they don't have it. Another one, someone didn't have COVID and you said they have it. दोनों ही problematic है. Then you weigh which one is more important for us. Yeah. So that will depend on the situation. But we have a name for these. This one we call type 1 error. Of course, these two are errors. These two are correct conclusions. This is called type 1 error and this is called type 2 error. A false negative is type 1 error. Wrongly rejecting null hypothesis. That is type 1 error. Type 2 error is mistakenly accepting null hypothesis when in fact it was false. Yeah, that is type 2 error. Total probability of being wrong is of course the sum of these probabilities. So let's see. Let's name them also. Of course, we are dealing with probabilities. So far, we just wrote the cases. We will call the probability of type 1 error. We will give it a name. We will call it alpha. It's not equal to alpha, it is represented by. So, probability of type 1 error in literature, we usually call it alpha. Probability of type 2 error, as you can guess, probably we call it beta. Yeah. So from here on we will start using these also. Again, false negative, type 1 error, alpha, all equivalent in this field. Yeah, all have the same name, same meaning. Okay, so let's look at the case that we were discussing just now about the claim about heights of people. So in that example, remember I had set the range to, so my claim, if I remember correctly here, was that the average height of the adults is 165 and I set a range 164 to 166. If you fall within this, yeah, so you say I was right, otherwise you say I was wrong. And if 90% of you fall in here, then with 90% surety I can say I was right. Yeah. So in this case, what is alpha? Can anybody write it now? Help me write it mathematically. Type 1 error. Yes. So what is it? It's a probability on x bar. Yes. क्या होगा? Firstly, type 1 error, where will we make it? What was type 1 error? False negative. Yes? False negative. False positive was type 2 error. Yeah? False negative doesn't. So, where would one of you fall when they conclude that I was wrong? Where should you be?
You should fall in between.
Now, if you are to conclude I was wrong, if your estimates give you values here,
Above.
yes, outside. So probability x bar is less than 164. What are the chances of that? Okay, those are the chances that you will conclude I was wrong. So probability x bar is less than 164 when, sometimes we write it with given, when h naught true. So is that all, or do we need something else in false
Greater than.
negative? Yes. So there is another mutually exclusive possibility See, there are two ways you will wrongly reject me. Yeah. First is if you find your x bar to be below 164 when actually I was right, or if you find your x4 to be above 166 when I was actually right. So if you find it to be above 166 when in fact I was right, that is the second part of this error. So these two together in this example, remember, there is no fixed formula for alpha. It just says alpha is probability of type 1 error. Yeah, the nature of the formulation will then help you write this out further. Okay, what level you select, is it two-sided, one-sided, all that. So in this case, this is what's happening. What about beta? What was beta?
False positive.
Probability of, yes, false positive. Yeah. So now can you help me write what should be beta? What is it in words? False positive, है ना? You conclude that I was right when in fact I was wrong. Yeah. So how do you write it?
Greater than 164 and less than 166.
So, great, yeah. So you fall in here. Yes. The probability that your estimate falls in this range, x bar is greater than 164, less than 166. When, this is important, it's not just this thing. When h naught was false.
Sir, H high false mean
This is probability, it is false positive, yeah. So you conclude in my favor, yes, when I was actually wrong. So यही होगा. Okay. So since you will end up in this range, you will be in critical region. Your conclusion will be I was right. Yes. But when will your conclusion be wrong? And I was actually wrong. Yeah. So h naught is false, or you could say h1 true, if you want to. I write it like this. Now you could have a very specific value for alternate hypothesis also. Like if you say that alternate hypothesis says that the mean is 170 centimeter, then you can rewrite this more specifically. You could say, okay, probability x bar falls in 164 to 166 when in fact the mean was 170, meaning h1 was correct. Yeah. So you can make it more specific if you like, but the idea is the same. Now we have names for some more of these things. Firstly, the probability of true negative. Yeah. Probability of true negative, we call it is this. It is probability reject h naught when h naught is false, or you can say h1 is true. This is true. Remember, alpha and beta are about errors. Yeah, false negative and false positive. This is about true negative. You say h naught is wrong when h1 is true, which is that you're right. Yeah. So this thing has a name. We call it the power of the test. Okay. We define it as the power of the test. So we define type 1 error, type 2 error, and now this one, which is true negative, and we call it the power. The power of the test shows us its ability to reject the wrong hypothesis. Okay, so it has great meaning inside it. That's why it can resolve between correct and incorrect. ये वाला? We always assume if alternate hypothesis is true, then the first one is automatically false. H1 क्या है? H0 क्या है? You could either write it like this or write it H0 false. H0 false. Yeah, वो आपको overlapping hypothesis allowed नहीं है. Okay, so मतलब उसका भी कर सकते हैं कुछ, लेकिन एटलीस्ट अभी हम right. So this is called the power, and the alpha that we saw, probability of type 1 error, also has another name which we call significance level. We will see why it's called alpha. ये वही वाला alpha जो हमने confidence interval में देखा था, 1 minus alpha. Okay, so it's actually linked to that one, but we will see that later today. Now the question is, we just wrote them out. Yeah, हमने क्या किया? 4 possibilities बनाई हैं. Yes, table बनाया. Your conclusion and the real world. Your conclusion, H0 is wrong, or H0 is right. Real world, H0 is wrong, H0 is right. That led us to 4 possibilities. Yes, we called the error 1 type 1 error, type 2 error, and one of the possibility where you were right, that is you rejected H0 correctly, we named it power. Yeah, and then this guy we also named relative significance, but we didn't calculate the probabilities yet. Calculate तो नहीं की ना हमने कोई, we're just writing them out. Yeah. Now of course the real thing lies in finding a value here. Yeah. Now as you can guess, of course there is no general answer to this. Finding a probability of a random variable requires what? Information about its distribution, right? So depending on the distribution of the random variable, you will conclude or calculate different probabilities. So far we have just established the very general framework of hypothesis testing for 2 hypothesis cases. Yeah, there are of course multiple hypothesis cases also. We will not cover those in this course. So now to actually calculate these, the answer will depend on what kind of statistic you are talking about. So let's restrict ourselves to one case then. Up to here is general. What we did up to here applies to any hypothesis testing. These concepts of null hypothesis, alternate hypothesis, true, positive, false, negative, significance, power, that these are very general. Critical region, critical values, they apply to any hypothesis. After that, to actually calculate these p values, these p probability values, we need to decide, okay, which statistic are talking about. Why? Because we have been seeing in previous topics also that if you're talking about the mean of the population, sample mean, we know if you know the variance, then the sample mean is normally distributed. If you don't know the variance, then the mean is, what's it distributed? T distributed. Yeah. So our variance, we saw that it is chi-square distributed. So each one has its own distribution, and then there are others. F distribution, वो सारे आते हैं. I didn't cover because conceptually they are similar. So we have to restrict ourselves to one of them to really go further. Yeah. But what we do next is also can be repeated for different distributions. That's fine. So let's restrict ourselves to the sample mean. Okay. And in the previous 2 lectures, we have seen in great detail that the sample mean of from a population with a sample n, we defined it as xi. You just simply take n samples from the population, you average that, and that is your sample mean. Yeah. Now we have seen it that in fact this guy, if the true, let's say the true mean mu is the true mean and sigma is the true sigma square is the true variance and it is known, then we had shown that x bar in fact has a Gaussian distribution. It's normally distributed with mean equal to the true mean and variance equal to sigma square over n, where n was the size of your sample. So we discussed that in previous two lectures. We also saw why this is a good estimator. It's unbiased and it has a very low variance which can be made even smaller by increasing the size of the sample. So we covered all of that before. Here I'm just going to use that result. Okay. So for the sample mean, I do know the distribution, yeah, which is it is Gaussian distributed with, if the variance of the sample of the true population is known, then you can write it as this thing. But then how can this help us now write our problem more specifically? So let's see. Let's start with this thing, that clear this away, and let us start with a hypothesis about the mean of a population. Let's say my claim is that a particular population, the heights of adults in Swabi are mu naught, as I said 165 centimeter for example. I fix it to somewhere. Then the null hypothesis would be, could be actually, it could be something else also. One of the possibilities to say, okay, no, it's not mu. That's one possibility. Or you could say, one hypothesis that mu is equal to mu1, where mu naught is not equal to mu1. Yeah, you look the same hypothesis. So you could be specific or you could be non-specific. That's fine. Now, we now know that if this is true, then we know that x bar, as I already said, has a Gaussian distribution with mean mu and variance sigma square over n, assuming that the variance is known. Okay. So now remember we said I will say that I was right if 90% of you come back to me with a value between 164 and 160 within the critical region. Yeah. So we come back to that and we say, okay, let's accept h naught if x bar lies within a region a comma b with probability 1 minus alpha %. We'll have to make, remember we had to make this assumption. Yeah. So let's accept h naught if x bar is between a and b with, I said 90%, remember? So 90% of you say that I was right, then I was right with 90% confidence. So a common value for a and b that we use is, or notation we use is that, okay, this is mu naught minus z alpha by 2 sigma over square root n, and b is mu naught plus z alpha by 2 sigma over square root n. Nothing to get scared about. Remember what we said? There was this guy. I said height is 165, but then I said exact is difficult, so we will choose a range. Within that range, if 90% of you fall here, then I was right. Yeah. So now the only thing I say is mu naught is 165, and we have a more generic term around mu naught. So this is my claim. This is the critical region, which now we are defining as mu naught minus some z alpha by 2 sigma by square root n, and mu naught plus z alpha by 2 sigma by square root n. This z alpha by 2 we have covered in previous lectures. Nothing to worry about, it's just a level. You can adjust it to make this interval smaller or bigger. Yeah. So now we are saying this is my critical region. Okay, so we are now handling things more mathematically. So let's remove all of these. So now let's write that with more radically. We say except H naught if probability x bar is mu naught minus z alpha by 2 sigma over square root n and mu naught plus z alpha by 2 sigma over square root n when h naught is correct or true. This is the same thing we wrote before. We said p x bar is between 164 and 1, for example. Yeah, so it's the same thing that we're writing now. Now we can, and of course this probability has to come equal to 1 minus alpha. So what are we saying? We're saying we will accept h naught if the estimate of the sample mean comes out in this critical region with probability 1 minus alpha. It's like the same thing we said, 90%, so you can convert that. Now let's make it further precise. I can play this trick now, which we already did in previous lectures, that I can make it x bar minus mu naught divided by sigma over square root n is greater than minus z alpha by 2 and less than z alpha by 2 equals 1 minus alpha. Okay. Now, if my null hypothesis was correct, this thing must be standard normal. Yeah. So this thing should have mean 0 and variance 1, because if my null hypothesis was correct, then x bar is actually coming from Gaussian distribution with mean mu and variance sigma square by n. I can make use of this result. Now if I make use of this result, all you have to do now is select your significance level. Yes, put your sample size here, put your variance of the sample here, put your guess here, and find z from the table. Okay, we will do that for a specific example afterwards, but essentially you are saying, what are you saying? You are saying that you defined a region and you said that the probability, if I was wrong, if I was right, then the true mean is of course here at mu naught, and this is A, B, those the significance as the critical values, and to fall in here with probability 1 minus alpha, whereas the probabilities of these are alpha by 2 and alpha by 2, which is the total probability of a false negative. Yeah. So what we have managed to do is start from here. दोबारा से जरा ये पता है थोड़ा सा हो जाता है We said the null hypothesis is that the mean is mu naught. Alternate hypothesis mean is not mu naught. Said okay, let's accept h naught if x bar falls between a and b with confidence level 1 minus alpha percent, like 95%. Then we said okay, one good measure for a and b would be to have them around the mean, my estimate of the mean. And if my null hypothesis is correct, then our discussion from previous lectures tells us that the x bar will actually be normally distributed with mean mu and variance sigma square over n, where mu is a true mean. That is the case, then we can go one step further. We can rewrite that whole thing like this when h naught is correct. And we can go one step further. Use this information in our calculation here to come to this conclusion. And now it's just a matter of reading the value from the z table to find okay, what is the probability that of accepting h naught correctly. Yes, so let's look at now. The same thing can be repeated with t distribution and chi-square distribution, right? I won't do that here. You can look at it carefully in the book if you like. It's basically let's do this with a specific example now, yeah, so that before you get completely lost, you maybe get it a bit locked. So we'll keep these here as reference. Let's say that the null hypothesis is that average weight of male students is 68 kilograms. Yeah. So your null hypothesis is that the average weight of male students at GT is 68 kg. Yeah. Now we could say okay, let's say our alternate hypothesis is that that is not true. Okay, it's not 68. Let's say. Okay. Now let's assume that you take samples size of 36. You measure or get weights of 36 male students on campus. Yeah, because in real problems you will have to set these. कितने measurements लेनी है, कितनी observation लेनी है, और क्या set करना पड़ेगा, range set करनी पड़ेगी to be concluded to be correct. So let's say we set the range, the critical region, to be 67, 69. Yeah. So if your estimate comes out between these two values, you will say I was right. Yeah. Now how many of you should come to that conclusion? We have to set a level of confidence. Let's say I want to set a confidence level of could set it to 95%, but let's come to that after this. Now further assume that you know the true variance of the true standard deviation in this case is 3.6. So you know these things, and now we want you to discuss alpha, beta significance level for this particular case. क्या है scenario of you made a hypothesis about a population. The population is the male students on campus. Your hypothesis is that their average weight is 68 kg. By the way, we are working with average because it's easier than other cases to develop the concept. You don't have to make about the average all the time. Yeah, कुछ भी हो सकता है. Null hypothesis, okay, it could easily be a different null hypothesis. For example, that H1 says no, थोड़े से भारी हैं, 70 kg के. Yeah, somebody may have their own null hypothesis. Yeah, but let's start with this and we'll come back to this case later. So then we say, okay, we have to establish some realistic parameter. Let's say you measure weights of 36 of the male students selected randomly, and you say that the critical region is 67 to 69. Yeah, if you find the weights to be within that range, you say I was right. And let's say we know the variance of the true weights, true population weights. If we don't know it, what do? We replace it with estimate S, and then all of the next we do will not use normal distribution, it will use T distribution. Yeah. So that changes, but otherwise it's the same story. Okay, let's say what can we say about alpha in this case? Remember alpha क्या था? Probability of type 1 error. Type 1 error क्या था? False negative, wrongly rejecting the null hypothesis. So you can write it in many ways. Here I am going to say, let's say it is reject H naught when H naught true, false negative. Yes, data type 1 error. So can you help me write in mathematics now? What is this? इस केस के लिए क्या होगा? या जो आपने पहले क्या था, probability x bar is less than 67 when h naught is true, plus probability x bar is greater than 69 when h naught is true. Yes. Now, what do we mean by h naught true? You could also write it as saying that what we mean is that mu is actually 68. That mu is actually 68. Yeah, that's not true. Yeah, the mu is actually 68. Now, to calculate these properties, we will need to, or these probabilities, we'll need to talk about the distribution of x bar when h naught is true. Okay, so if x naught is true, that is, let's say, now let's look at this world where h naught is true. That is, true mean is in fact 68 kt. Yeah, true mean mu equals your guess. Yeah? If h naught is true, from our understanding of probability theory and the topics we covered already, we know that if h naught is true, then x bar has a Gaussian distribution under h naught. Okay? इसकी distribution क्या है? Gaussian है. इसकी distribution even if h naught is true is still Gaussian. But here is the critical difference, that the distribution is Gaussian and its mean is what you claim to be. ये critical बात है. Okay? X bar, the way we studied it, always have Gaussian distributed. Yeah? But the mean will change. And if you were right, then the mean of this is actually 68. ये critical point है यहाँ पे. Sigma over square root n, or sigma, if you want to write the variance, you can replace the, some books use variance here, some use standard deviation, that's why I get confused. I'm more used to variance. Your books uses standard deviation, which is the square root of that. So anyway, okay, so this is the distribution of x bar. Okay, now what we wrote here, this one, x bar less than 67 when h naught true, plus x bar greater than 69 when h naught is true. What does that represent? So have here 67, 69, yes, and you set this to 1 minus alpha. You want this area to be 1 minus alpha because you want these areas to be alpha by 2 and alpha by 2. यही हो रहा है ना यहाँ पे. Total alpha, it is metric, so this part is alpha by 2 plus alpha by 2 makes alpha, right? The total probability of type 1 error, right? So coming to this thing, now we know, okay, then I can write this now like this. This is probability. Let's talk about one of those values. X bar is less than 67 when the true mean is 68, that is null hypothesis is correct, is the same as saying that probability X bar is less than 67 when X bar is distributed with normal and 68 and sigma over square root n, whatever values you are given. Now this thing I can rewrite as probability X bar minus something wrong here, this is less than 3. X bar minus 67 divided by sigma over square root n is less than 68, sorry, the true mean. 67 minus 68 over sigma square root n. So we are slowly rewriting it in terms that we understand. ये term कहाँ से आई है? This is the first term here. ये वाली. I'm just calculating the first part. Yeah, we know it's metric, so the other will have the same value. So let's look at that one. We were able to write it mathematically here. Since we wrote it like that, we can make it even simpler and say this equals probability X bar minus 68 over sigma square root n is less than, I will replace these by their values. Do we know sigma from our problem statement? It was 3.6. Yes. Do we know n? It was 36. So we can put those values there. So now I'm going to do that to really get numerical values. 3.6 by 6, and here if you calculate the right hand side, it comes out to be minus 1.67. Okay. Now since we already know that this is standard normal, then this is your small z, and you can read the standard normal table fz against z. Yeah, so you have z, find it, read what value you get, that will be placed here, and that turns out to be, if you read the table correctly, I calculate that or not? Okay, I didn't write it here, but whatever value you get, you put that here, and then you do the second term, which is actually the same value as this one. It turns out to be, the whole thing turns out to be 0.0950 or 9.5%. This is alpha. Okay, if you do all those calculations, you end up with this value. What is it saying? Probability of what? Type 1 error. Yes. What is type 1 error? That you wrongly reject H naught. Yes. False negative. Yeah. क्या आई इस केस में? 9.5% आई, right? So the probability of wrongly rejecting the null hypothesis in this case is 9.5%. Now, can I make this better? क्या करना पड़ेगा? Well, if you look at it here, notice this thing, there is an n here. So if you increase the sample size, yeah, you will see that the variation will become smaller and overall this value will go higher. For example, if you were working, this was found using n equals 36, a sample size of 36. But if you repeat this same problem with a sample size of 64, yeah, you will actually get the probability of type 1 error 2.64%. Okay, why is that? Again, that is because if you increase the n, the variance decreases. Okay, as the variance decreases, more of the data enters this region, which is the region of acceptance. Yes, so the probability of making that type 1 error becomes smaller. What's another way of increasing alpha without playing with the variance or the sample size? Would be to increase this range. Yes, to be less strict. You could say, okay, I will say I was right if you find the height weights to be between 66 and 70, but usually you don't want to do that, not make it too loose. Yeah, so the idea of increasing sample size makes more sense, so you can use that and come here. Now similarly you could calculate beta, for example. Let's do that and then we'll end the lecture. Almost there. So what about beta? Beta क्या था याद है? Type 2 error. Yes, what was type 2 error?
False negative. So false positive.
False positive. Yeah. So let's say this thing very briefly. Everything else is the same, but now I want to have a specific beta. So usually it helps for beta to have a specific alternate hypothesis. So this hypothesis is H0, the average weight of male students on campus is 68. The alternate hypothesis is no, it is 70. Yeah. So with that, let's try to calculate beta. Now beta we said was probability of false positive. That is, you concluding that they are actually weight is 68, whereas their average weight is actually 70. Yeah. So that is probability except H0 when H1 is true. Okay. Now in the case that we just solved, ये जो case था, assuming the ranges are the same, the sample size is the same, how can we write this now mathematically? Probability acceptance range क्या थी? 67 to 69. Let's say acceptance range is same, sample size is same, whatever it was, and whatever sigma was is the same as what we just solved for. Then in that case you can see quite easily that this is what would be called the probability of false positive, which is that X bar falls in your acceptance region even when it shouldn't have. Yeah, even when H0 is false, or in this case for convenience we just say even when H1 is true. So X bar is falling in your acceptance range of H0, so you will accept it. Yes, but H1 was true. That will lead to this error. That is the case, then the probability, this probability can be written as X bar between 67 and 69 when in fact X bar had a distribution with mean 70 and variance sigma over square root n. This is where the difference lies. If the true mean is 70, that is h1 is true, then it is still Gaussian distributed, but its mean should be 70, not 68. पीछे कैलकुलेशन में हमने 68 क्यों यूज किया यहाँ पे? Because all these calculations were done saying when h not true. ये बड़ा अहम फर्क है. Okay, if h not is true, you are talking about x bar being Gaussian distributed with mean 68. If h not is true. Okay, if h not is false, then you are talking about x bar being Gaussian distributed but with a mean 70 if the alternate is true. Yeah, so the distribution shifts depending on the hypothesis h naught or h1. So in all these calculations they were based on when h naught, इसलिए ये important है ये लिखना साथ. Yeah, when h naught is true, work with this figure. When h1 is true, given h1 is true, conditional cases, then you have to work with the other case. So now you can just redo this now. So this probability, this is going to be equal to probability x bar minus 70 divided by sigma over square root n is less or equal to or greater or equal to 67 minus 70 divided by sigma over square root n and 69 minus 70 divided by sigma over square root n. Notice पिछले step में in the previous case we used 68 here. Yes, we were assuming h naught to be true. Now we are assuming h1 to be true. So then we have to use whatever mean the h1 claims, which is 70. So you will calculate this and you will get your beta, whatever that value comes out to be. I'll just make a diagram showing what really happened just now. And this is the reality now. There was one claim that the mean is 68 kg. There was an alternate claim that the mean is 70 kg. From our understanding of probability theory of the sample estimate, we know that if this is true, then the sample estimate will have a Gaussian shape that will be, oh, it is right. Okay, let's do that. Will be, the mean will be here. This is when h naught is true. When h1 is true, it will look like this. Same weight, same variance, everything same, except that the mean has shifted. This is h1. Can any of you tell me, okay, what was our acceptance region? It was 67 to 69. Right? Now can any of you tell me here in the graph which area should represent beta? Probability of क्या था? False positive? Yes?
Yes, sir.
कौन सा एरिया होगा? बस ये आखिरी सवाल है, इसके बाद आप ठीक है.
सर ये 70 है.
70 वाला कहाँ से कहाँ था?
सर 69 से लेके 71. 68 से लेके
शुरू 69 से होना है, ये ठीक है. और इस कर्व का एरिया इसका नहीं पढ़ना. क्यों? क्योंकि when you are calculating this, you are assuming which curve is correct? This one. Yes? False positive यही है ना? Accepting h naught when h1 is correct. So you are assuming this to be correct. So कौन सा एरिया है? This area. ये जो कर्व जा रहा है ना आपका, इसका ये जो एरिया लीक कर रहा है ना into your region of acceptance. क्योंकि क्या हुआ है? Basically, you said I will favor this hypothesis if you are in this region. Problem is that even when H1 is correct, with this much probability जो भी area है ये वाला sorry ये नहीं आएगा
H not भी correct है इतना
इसमें H not तो correct आता है लेकिन even if H1 is correct, with this much area with this much probability you will fall in the region of acceptance and you will be led to type 2 error, which is with this much probability you will conclude that H1 not was correct because you fell in here in this region, but you were wrong. Yeah, why you were wrong? Because actual one was that H1 was true. Okay, so इस पे जरा दोबारा सोचना.
तो इसकी significance मतलब कि थोड़ी है लेकिन ये इधर भी fall करता है ये.
हाँ, right. This value will come out to be small. Yeah, that is fine. But what we want to calculate is how much is it. Yeah, and that will be beta. Compare this to alpha. Alpha क्या था? This was alpha. This was the curve for H naught. है ना? This was alpha. The likelihood of you falling in the right, not falling outside the region of convergence, critical region when H naught is true. Yeah. So there you only look at this curve. But if you want to study the alternate hypothesis, then you have to study this area. What's happening here? This is saying what is the likelihood. ये जो line है ना, ये बता रही है कि what is the likelihood of your estimate falling here, here, here. With these probabilities, it falls here, even when H1 is true. तो फिर ये सारी की सारी जितनी दफ़ा आप इस रीजन में होंगे तो सारे आपके गलत डिसीजन निकलेंगे, right? So you want that to be low also. Okay, so these are two ways of working. Sometimes you want to, often ये होता है कि आप एक को कम करते हैं ना तो दूसरा बढ़ता है. Okay? If you try to reduce type 1 error, type 2 goes up often. Okay, so usually it's a trade-off. Yeah, so at an airport, let's say there is a detector of narcotics or something, कोई machine है उसमें से आपका सामान गुजरता है. So which one would you like to be reduced? Type 1 error or type 2 error? अगर let's say narcotics की बात करें, असले की बात हो रही है.
False positive.
You would try to reduce false positive. क्यों?
ये वो गलत positive था जैसे मैं हूँ.
हर दूसरे बंदे पे वो टीटी करे, फिर तो आप यूज करना भी छोड़ देंगे, बाद में या हर बंदे की चेकिंग करेंगे, राइट? तो लोग क्या होगा, क्यूज लंबी हो जाएंगी. यस, असले के मामले में मे बी यू कैन गो फॉर another case, yeah, because if somebody is carrying a gun on an aeroplane, that's maybe more scary thing to hijack करना है या क्या करना है. So there you might be more interested in avoiding false negative. Yeah. So situation decide करती है. Yeah. But in most cases you cannot have both. Okay. So एक को करते हैं दूसरा adjust करना पड़ता है. And these are not by the only two ways to test or decide. There is something called a p-value. I'll just leave that as a reading exercise. But with that, we have the fourth module of the course completed. Next lecture, we will look at the final module. It will just be an introductory thing, which is statistical modeling. Okay. So far we have been only talking about the mean variance of data. What if I want to predict the data? Exact value क्या आएगी? Next बंदे की height की value क्या आएगी? अभी तक हमने उसको probability assign की, probability distribution assign की. But can I say, okay, it will be 75, 78? Exact values क्या आ सकती हैं? So I want to make a model for that and use that to predict. Okay, so that is the last module of this course, inshallah, Wednesday.
तो ये फाइनल से सिलेबस बहुत ज़्यादा नहीं है. आज दिया है मैंने
फाइनल का